All right. So who's Ben? Are you giving the presentation today?
That's me. Yeah, that's me.
Okay. So Ben, can you please introduce yourself and then, with no further ado, continue into your presentation?
Sure. Yeah, thank you to the Open Compute Project for having me here today. Hopefully, I'm sharing the right screen here. So yeah, I was invited to give this talk just to give a maybe different perspective on how or an application of where PTP is used in display-based applications. By way of introduction, I'm from Intel. I'm a technologist in our Edge group, and my responsibility is looking at the professional AV industry and also our heterogeneous compute portfolio and guiding some of the roadmap and other investments we need to make to support that industry with Intel products. Um, with me today, there's a couple of other Intel colleagues who've joined, who have various roles. In particular, just wanted to introduce Satishwar and Ashay here. They're some of my colleagues in our organization who've been working on the technology with me that we'll talk about today, and they may say a few words as we go through. Um, so yeah, let me get started. So, as motivation for what I'm going to talk about today, I'm just going to refer to a white paper here we did with Panasonic recently and a partner, Hive, who do media servers. So the picture here is the BBC Earth experience in Melbourne, which was a touring exhibit in Melbourne. And essentially, the technology we'll talk about today that we enabled was used in this exhibit. And what you're seeing here is a projection from almost 100 Panasonic projectors across the whole installation. And the key challenge, obviously, is as those are projected from different projectors, you need to keep the video output from them in very high synchronization. Actually, the worst enemy or the biggest challenge is people taking pictures with their phone for social media. Because if you take a still image of moving video that has some artifacts, it can really enhance the visibility of that artifact. And I'll show some examples later. Um, Now, what we did in doing this synchronization, so the synchronization was the key thing we enabled, but what this has also enabled, which is sort of the title of the paper, is it's enabled the way in which the compute for these type of installations is done to change. And I'll sort of talk a bit more about this on the next slide. So um, traditionally in these installations, you would have a rack of server server equipment with many high-end graphics cards, which would uh, generate all that content and output it where it is very highly synchronized at source. And we'll sort of talk a bit about how graphics cards traditionally do that later. And then on top of that, you would have extender equipment, typically today extending over IP networks using protocols like SMPTE 2110 to then extend the content to the projectors so that over those networks they stay in sync. And as you can imagine, that sort of left-hand picture here of those servers with many graphics cards in them, extender equipment is very complex and to install and also quite expensive. And if this is a touring exhibit like that BBC example, that can be particularly challenging for clients because that needs to be teared down and taken to somewhere else. And if you imagined that was for a concert or something, then again, that challenge is amplified. So what this synchronization approach we'll talk about later enables is it enables us to, instead of having this centralized compute, put the compute within each one of the projectors. And the company Hive I mentioned has created some media servers using a standard that Intel defined called smart display modules, which will slot into the projectors. So it means all that compute on the left is replaced by compute within each of the projectors. And the novelty we bring is to be able to highly accurately synchronize the outputs from those distributed projectors. And that's just using the local Ethernet network to do the synchronization using precision time protocol and some other enhancements we'll talk about a bit later. The headline of this, of what this, of the impact for customers is, in this case, as you see in the quote at the bottom, the CAPEX saving for the equipment was reduced 30 to 40%. And then obviously on top of that, we have the significant saving in installation cost as well. So that's going to motivate why it's important for us to look at things like the synchronization I'll talk about here. Please stop me with any questions as we go through. I just want to show this as well. So what I showed on that first foil was one use case, immersive exhibits, and that's with projectors. So that's clearly one application of the need for this distributed synchronization. But we also see needs across other use cases and display mediums. So I just pulled a couple of pictures here to represent that. So if you think of in control rooms, you have a similar scenario where you have a wall of displays and you either want to use those as individual displays to view, for example, different IP streams and different security cameras, or maybe you want to blow one of those up on the wall or on part of the wall, and then blowing those up there, you need to similarly synchronize the content. And then, so that's sort of in sort of traditional large format displays. You also see the requirement, and actually it becomes even more prominent in things like direct view LED. So you'll probably recognize the right-hand picture of the Sphere in Las Vegas. That was an image I found on the source there of when Intel took that over at CES. But in that scenario, you have many tiles, and these tiles in these installs are maybe 256 by 256 pixels or quite relatively small to the size of these installs. And the content to each one of those needs to also be kept highly synchronized. So this challenge is across many use cases and many different display mediums. So if I sort of get more into the sort of technical side of this, of where synchronization is needed, I take this picture as an abstract from an Information Display Magazine article that I'll provide the details of at the end of the presentation. What I summarize on this picture is associated with video walls, all the different scenarios in which synchronization comes into play, where you need to synchronize links or between different displays. And we'll sort of start on the left-hand side. So the top left over here is that sort of centralized architecture. So the first thing to note is in these displays, you may have in scenarios such as a film studio, you may have a camera actually filming the display. So if you have a camera filming a display, you need to synchronize that camera's capture to the display. Otherwise, you get a flicker effect. So you can try and emulate that by recording a display from your mobile phone. And if you play that back, you'll see the light flickering because the rate of capture is different from the rate of display. So that is one scenario. Secondly, for these centralized media servers, this picture below depicts graphics cards, each with multiple outputs. And what you typically do on these graphics cards to synchronize them is pass cables or wiring between them to tie the clocks and the video timing together to synchronize them. So that's another scenario. Thirdly, you have these AV over IP networks, so where you generate these outputs, but a HDMI cable cannot be very long, right? Maybe you can get 3-5 meters. You certainly can't get 100 meters or 20 meters, which might be the distance between the server and these walls in big installs. So you would use these extenders over IP networks. And those, of course, need to be kept in sync. So if you've synchronized all the source, you need to keep that in sync as the content gets to the display. And then switching to the right over here, this top right picture is that sort of distributed architecture I talked about that we'll sort of focus on in this paper. In this case, you have a media player behind each display, And if you want that content to look good across the whole display surface on those multiple displays, that also needs synchronizing. And then finally, the bottom right here is the typical compute architecture of those LED video walls. So this is generalized from a few companies' way of doing this, and you have these modules on the right-hand side over here that are pieced together to make the LED wall. Each of these is connected today from a controller using Cat6 cables, RJ45. Now, there is a mix in the industry. A lot of people are using a sort of proprietary protocol here, but areas we've looked at, it's maybe a topic for another time, is how to do this using standard IP traffic. And again, if you're doing that with standard IP traffic to drive these modules, again, you need to use something like PTP here to synchronize them. So from those pictures, and I can provide these slides and article afterwards if of interest. But this sort of summarizes from that picture before the different places in a video wall where synchronization is important. So firstly, that sort of centralized media player output, where we're trying to lock the frames across GPU cards. And industry example over here is this is a feature we support on our Intel graphics GPUs, enabled with a company called Matrox, done that. Secondly is that synchronization to the cameras I talked about, where you're recording the display. In this, you would typically use a black burst time synchronization that would happen in the studio, or so more recently, precision time protocols being used by vendors for this. And an example is NVIDIA have their Quadro Sync card, which does this, which allows that external reference. Also allows them to tie multiple servers together to synchronize those as well. The synchronization of extenders. So for that extension challenge, this has particularly come about because people have replaced HDBaseT or SDI, which are more point-to-point type connections with IP. So these need to go through PTP-aware switches. And this is something which is supported in industry standards for AV over IP, such as SMPTE 2110. There's a PTP profile for that. And also it's a feature in IPMX, which is a sort of derivation of SMPTE 2110 to target the professional AV industry. And Intel has a media transport library that helps customers to implement these protocols on our Ethernet cards and processors. On this side here, on the synchronization of distributed media players, this is where you synchronize across PTP networks, and people do this do kind of parts of this today. But this is what I'll talk about in our solution a bit later. This is what we've targeted in the innovation that sparked Dan's interest when he sort of introduced me to talk here. We have reference code on that's available for this. For this, we call our software gen local software synchronization approach. And finally, the LED controllers. This, as I said earlier, can use proprietary methods to keep in sync today. But there is movement to use more open Ethernet type approaches. And as an example of this, we had a proof of concept we published in a paper at Display Week, which is the reference here, which is findable through the paper, that shows the use of PTP to synchronize LED tile video walls as well. So this was a picture I showed before, just to tie the couple of bits of the intro together there. So the before architecture I mentioned in that BBC Earth experience scenario, or the traditional architecture, is this left-hand side here where you're using that centralized equipment, maybe extending content over an IP network. So that was that kind of graphic here I showed. And then the after architecture, which is the innovation we're talking about here, is the right-hand side picture over here. So now I'm going to describe how we do this synchronization between the distributed media players and sort of talk through some of the technical aspects of how we achieve that and what we're trying to do. So we're kind of double clicking in on this side over here. So firstly, again, apologies if this is very fundamental for some people on the call, but I didn't want to assume we had video experts on all video people on the call. So I thought I would start here. This is an important concept to be aware of video interfaces such as HDMI, because this is what we leverage to help us synchronize the display outputs of those distributed media players. So on the left-hand side, I show how video timing is communicated over baseband video interfaces like HDMI, DisplayPort. It's the SDI uses something similar, where you have VSync and HSync signaling, which will communicate the exact timing at which the interface is saying there's an active picture on there. And that's what's used to accurately communicate the frame rate and the resolution of a video over the cable. So that is very important because, and for the purpose here, you can just think of those video timing signals as that sort of cadence of when the frames are occurring. The second aspect, which is important to understand, is that over these interfaces, you need to communicate some understanding of the clock, of what the clock rate of that signal is. And in HDMI 2.0, there's a separate TNDS line, which is the clock channel, which is communicating the clock. And I'll come back onto that a little bit later as to what we do with this. But that's just important to understand for now, that there is a clock there that could be modulated. So what are we trying to achieve with synchronizing these distributed players? So as I said before, you're trying to get that contiguous video across all the display outputs so that you don't have any tearing. And I've got a video just showing what I mean by tearing in a minute, if that's not clear. So this is the starting scenario where you have primary, secondary, and tertiary systems, which are all running at slightly different interpretations of the time. So each one of them would have a HDMI output, but in very small fractions, they have a slightly different understanding of what, for example, 59.94 hertz is, and the clock associated with that. So you can't guarantee each of their understanding of 59.94 is the same because they have slightly different crystals and so on. So what we are trying to do is go from this base scenario, the starting scenario, where they all have these slightly different understandings of time, and line them all up on the right-hand side. So we're trying to get that cadence of the video timing output. If you remember the last foil, I talked about those VSync, HSync signaling. Essentially, you're trying to get all those to line up in time. So if we could view them all together, they've got to all look like they're overlaying and look the same. That's the objective here. So this video will just show a picture of the sort of effect of synchronized and not synchronized. So this is obviously quite extreme, but you see on the right-hand side over here, the video looks smoothly the same frames between the different displays. On the right-hand side over here, as I play the video, you will see that is drifting over time. And as we get further through the video, it kind of becomes unwatchable in the, we've kind of exaggerated a bit here, unwatchable in the synchronization difference between the displays. Oops. So this slide covers a bit of how traditional methods work. So you have these, and this is for reference to before. This is typically in that centralized scenario. How do we synchronize multiple graphics cards or maybe even multiple processors in that scenario? So you similarly have the primary, secondary, and tertiary systems you're looking to synchronize the output of, or graphics cards as these could be. And what vendors tend to have is a bespoke connector. So this can look like a small bit of cable or something that will connect between the cards or the systems. And what this is doing is passing a reference clock and video timing signal, the VSync signal I talked about before, between each of the clocks. So you can treat one of them as a primary and then the remaining systems base their own vsync signal and clock off that primary device. So you're inherently synchronizing them. Now, the way this works with Intel's GPUs is that this then creates a synchronization sort of at setup, at boot, and then once they are synchronized, they don't drift because you've got this inherent tie of the reference clock from the primary to the secondary and tertiary systems and that vsync timing. They all stay locked together. So it keeps everything locked at source with small variations to the uncertainties that get increased across cables. That's kind of the traditional method of how that works. The next slide, we're going to talk through how our Genlock approach works. So I'll explain high level, and then I'm going to ask Satishwar to talk through this diagram, given it's his, if he's okay to do that. So what we do with the distributed case is we start off with all the distributed systems having their common understanding of time. So they do this from each having a network interface card that supports PTP 88, and they can get a common time base at the CPU. Now, the challenge with sort of how the way the processor is architected there is that CPU clock is not in any way tied to the clock which is reading out of the display buffer to display. So even as you've got them all synchronized to a common understanding of time, the displays are still free running. So what we want to do then is on each of those systems is to read the display timing on each of them. So read those vsync signals, so we can essentially read how many frames have gone by on each of those, and then you can compare the count between the systems. And if you find your secondary system has output slightly more frames in a period of time than the primary one, then we want to slow down the clock output very slightly on that secondary system so that they come back in line. And of course, this is something that can drift over time, so we want to periodically do this. Satishwar, are you okay to talk through how the sort of software stack works here for this?
Sure, no problem, Ben.
Tell me when to animate. Yeah.
Yeah, so just keep building, I guess. So essentially, the way that the whole thing works is that we have these systems, secondary, tertiary, and this can be like infinite number of systems that you can connect to a single primary. They are basically just sending, network messages over to the primary system, and the primary would essentially create a thread for each client that connects to it. And then the job of the primary is to essentially provide each of these systems with its own vsync timestamp, the last vsync that happened. And from then onwards, the job of the primary is basically done. Right, the secondary or the tertiary systems, when they get that timestamp, they collect their own timestamp and they figure out how big of a delta do we have, right? So in the previous couple of slides, Ben was showing you guys how they could be off by some random number of milliseconds, and the goal is to essentially align all of them. So they find out first how big of a delta they have, and then this is where we essentially go about tuning the PHY's integer and fractional dividers such that the vsync would slightly be slower or faster. So as Ben was saying right earlier, that we were typically running at that 59.94 megahertz clock, and therefore each vsync is exactly at 16.66 milliseconds from each other. But due to this change that we have made to the fractional dividers, we essentially are now running at, let's say, 16.650, so 16 microseconds faster or 16 microseconds slower. And over time, this 16 microsecond would start accumulating such that the delta, let's say the delta was 4,000 microseconds, we would be able to get to that delta, so that there will be a time after a few seconds that the primary and the secondary are exactly on top of each other, right? Their vsyncs are happening right at exactly the same time. So we pre-calculate the time or the interval that will take for us to be right on top of each other, and then at that time we go back to the default values of the secondary so that the vsyncs start happening again at the 16,666 microsecond interval. And that way these systems are gonna hopefully stay in sync. Now, if you build one more time, Ben, what I'm trying to show here is that unfortunately the reference clock of these systems are their own, right? We do not share the reference clock. And because of the fact that the reference clock is indeed their own, that means that they will periodically drift from each other. And this is where, the customer can decide whatever their threshold is, right? So once we have, let's say we were off by 4 milliseconds to begin with. Now that we have done this, we've implemented this algorithm once, we have now gotten the two systems in sync with each other. And now the threshold is, let's say, 500 microseconds. So essentially, as and when the drift starts to happen and they start going above that threshold, we can essentially go back and re-implement this algorithm, meaning, ask again from the primary what its vsync timestamp is, go back, figure out the delta, and then use the fractional dividers to essentially go back and synchronize again. And that's how the whole thing can stay in sync for an infinite period of time. So this, in essence, is our software genlock approach.
Thanks, Adishwa. Okay. So I have a short video here which shows this this happening on a scope. So you see these are just the measures of those vsync timing, and what you see is that secondary system versus the first system, being out of sync and then being brought back in time. And then the resolution of the scopes obviously being increased as that gets closer, and you see that that tracking back to that tracking to sort of target bringing it back in line, and you'll have a small variation over time that it needs to keep tracking for that drift, like Satishra was saying. So this summarizes the value proposition, or the pros and cons, I suppose, between that traditional approach of centralized and the new approach we showed of distributing the compute. And to reminder, that's just a picture of the centralized one, to make sure that's clear. And actually, when we surveyed a number of customers, there's a very high interest in this distributed approach because of some of the cost reductions and simplifications it brings. So we actually have customers using this in across signage and control room like applications, and others looking to design this in at the moment. In that traditional centralized approach, you do get a arguably higher accuracy today. Somewhere around 64 pixel clocks is what we see, and without the need for that periodic resync. This distributed approach is slightly less accurate, to the order of I think a couple of lines is what our customers report, and need the periodic resync. But typically that is more than sufficient for the application, because even if you're photographing the screen, you don't tend to see that line of difference. So that's accurate enough. In the traditional centralized approach, you may have limitations on the number of displays, for example, 16. Whereas as Satishra was saying, in this distributed one, in theory, we can do any number. We know this has been deployed to at least 100 displays, around 100, but could go higher. The cost per system, from the example I showed before, is typically lower on the distributed versus centralized. In terms of support on Intel processors, that traditional hardware-based approach, you need dedicated logic in a processor or GPU to do this. So it's only supported on specific SKUs. So for us, we brought this in on the 12th generation of our core desktop processors. Something like, like if you look at NVIDIA graphics cards or our own, they'll only be supported on particular cards that are sold. So it's kind of has some hardware dependent aspect, whereas the distributed approach we talked about, in theory, can be implemented on any processor, maybe in the future GPU, because you don't have that hardware dependency. There's no dedicated cabling. You're using the Ethernet cable that's usually already there. This talks about the Intel products I mentioned. We don't currently do this distributed approach on our discrete GPUs. It is something we're investigating. And interestingly, this, whilst in the traditional sort of centralized approach, you typically want processors all of the same type because of that tying of the clock together. In this new approach, we believe we can take a heterogeneous configuration, so you can mix and match different processors because of the way you're going about the solution. And today we, for a few reasons, the traditional approach we enabled in Windows, whereas this new distributed approach we've just enabled in Linux. But the converse is under evaluation as to whether we, as to enabling on the other OSs in each case. So in summary, what we implemented with this synchronization approach is it enabled a architecture transformation to this distributed approach. You can see this at a high level. It helps with a democratization story where it enables, in this case, a move from you having to use custom hardware to standard PC graphics card hardware, which is very attractive to the industry. And then it's also, the solution is based off a novel technique with x86 to leverage PTP and video timing characteristics. The finer details of what we've done, we have some patent protection on. We didn't cover those today for good reasons. But that's it's based on it leverages that the video timing characteristics I mentioned. So just in wrap up, this is some further reading if anyone's interested. The white paper here, if you'd like a copy, I can send people a copy. I'll put my email address in the chat afterwards, or contactable through the Intel folk like Zolly, who are regularly on this call. And also there's an Information Display Magazine article from September-October edition here, which is free to download. Either I can provide the link, or Googling that will find the article, which goes into detail on the solution I talked about, and also those breadth of different places where you need synchronization in video wall that we covered as motivation. So thank you everyone for the attention, and they're happy to take any questions anyone has.
Does anyone have any questions?
I have a question, Ben. On slide 12, where you were, where Satyeshwar was giving the explanation, what happens if there's a failure in the primary?
So what exactly do you mean by failure? Like, as in it cannot collect its own timestamp?
Well, it has, yeah. If it no longer works for some reason, what happens?
Yeah, so maybe I can answer that, Steve. So what we enable with this is we're giving software partners the hooks to implement this. So we have partners who've written media player software, like Hive I mentioned before. So all we provided them was the way to access the PLLs and to modify the clock. Now, someone like that, and I'm not sure if Hive have done this or not, but in theory, what those people who take this into an application can do is, if they notice one of the systems has gone down, there is, they could switch to one of the other systems acting as that primary device. It's my expectation. So they could, because any of them could in theory act as that. That would just be a failover mechanism that they'd have to build into their software.
Okay, thank you.
Great question. Yeah.
Ben, what is the underlying PTP precision that you need for the synchronization to work? seamlessly?
I don't know. So it's a great question. I think anything more accurate will get you a finer accuracy to those couple of lines we're talking about before. I have had comment from people that they would potentially do this without a PTP aware switch on NTP, timing. Obviously, you would lose some accuracy of how tight you could keep things. You could keep the synchronization because you essentially write a PID controller to do the synchronization step. I don't know, Satishwar, if you had any experience that how tight you got it in our testing we did in the lab.
Yeah, so when I was testing it, basically I was using PTP4L and PHC2sys to get the wall clock synchronized, and they were getting the two systems to, let's say, 100 nanosecond accuracy.
Thank you.
I have a question. For the precision, what is the limits that you're looking for? Like you look for let's say, a percentage from the duration that you take for a frame, like a period of a frame, or is it I want to know what determines, let's say, the maximum error you can have in terms of clock skewness.
Yeah. So typically a couple of like 1 to 2 lines of inaccuracy, which I think Satishwar, we did translate that into seconds. I think what that was. But 1 to 2 lines in a 60 frame a second video is typically allowed. So you're trying to track to within that. The other sort of knob you've got to pay attention to is also what we referred to in how much you modify the clock. So the reason why Satishwar mentioned that small modification, which comes down to the speed of convergence. So we would maybe typically have a slower speed of convergence than what other scenarios might have, what other use cases might have, because we can't move the HDMI clock that quickly. Because if you move that HDMI clock by too much, it would potentially, make the display receiving SoC fall over. So you have to be careful how much you're modifying that as well. That's sort of another related consideration.
Yeah, so to add on to what Ben was saying, essentially it depends upon the resolution of your screen. But if you have let's say a 1920 by 1080, then each row is 15.4 microseconds. So if you have 1 to 2 rows, then it's essentially 15 to 30 odd microsecond that you want to synchronize to.
You're getting some cumulative inaccuracies through like the software stack we're running to do the tracking. So
yes,
you might need a higher accuracy PTP to the questions as Ollie was asking, and then because of the stack we're running to do the alignment, that introduces some more inaccuracy.
And another question is have you done, let's say, a heterogeneous implementation where you have, let's say, walls of LEDs, but then you have, let's say, some laser projector as well or something, and you're trying to make the scene created from, let's say, all these different things?
So what matters to us is not the type of display, but the type of PHY. So you can have different systems, that could be different types of PHY, like, for example, a decal PHY or a combo PHY. And we have indeed tested these different kind of systems together and made sure that they are all in sync. So we can go about doing that.
Yeah. And one last thing. Sorry, go ahead. Yeah.
I was going to add to your question on display types. We, from the compute side, we kind of don't care in that because we're synchronizing those HDMI outputs that are coming from the PC, and those will go to a display. The challenge you would have is that different displays have slightly different latencies through them, but so we've only, to answer this directly, it's only either been done with projection or large format displays today. It's not been done with other types or mixed in them. But if you did and you had those inaccuracies, because of the way the control's done, someone in their own application may be able to compensate for, one display type having a higher latency through the display processing than the other, which would add some more differences. But you need to compensate for that separately.
And then last question is like, is this also done on, let's say, live or real-time video stream coming in, or it's been always like on, let's say, recorded stuff?
So far, well, see,
It doesn't matter.
yeah.
It doesn't matter, what the content is, right? And we do it. We do it so that it is completely impervious to the end user, right? So they could be watching either recorded content or live content on their two screens or more than two screens. And what they don't know is behind the scenes, we are essentially getting all of these systems in sync with each other.
This is more, let's say, if you are, let's say in a concert or something, and then you're filming, let's say, I don't know, the singer or something, and then you're projecting their video straight on the screen.
Yeah.
Then every latency, counts.
Yeah, I think I kind of see where you're coming from. So Sisha's right that from the PC, what we're doing with the PC, it doesn't care. But what I think you're referring to is, and we haven't done yet, to be honest, is if you had an IP stream of video coming in, maybe you're using something like SMPTE 110, if you know the protocol where it will stream the video in. We haven't taken the time and reference from that and locked the display to that so far, which would maybe be how you do that sort of thing for minimum latency and for some to avoid some of the filming artifacts. That's maybe something someone could do with this. More the use cases we've had is like you saw with that BBC Earth one or a control room where we don't have that requirement. I think even if it's a control room and it was playing back IP camera traffic, it would just drop and repeat a frame as it needed to. It doesn't have that need to display absolutely every frame that you might have in those concert-like scenarios. It's maybe theoretically possible. We just haven't tried to do that yet, but maybe something we can do in the future.
Thank you.
Great questions, I thank you. Does anyone else have any other questions we can help with?
Right. Paul, is Paul still here?
Yeah, I'm still here.
Back to you.
Well, thank you. So Ben and Sashwa, that was a fantastic presentation. Thank you. And I don't really have any questions myself. I think I understand what you're doing. But I think that was very informative, from an engineering perspective on what we can do to try to understand video streams essentially. So thank you for that very much. I don't have any specific questions that are not physics related, which probably won't be appropriate here.
No, thank you for hosting this. Appreciate you recording and for everyone's time. I put my email in the chat if anyone wanted to follow up on these topics.
And I also put the It's About Time link into the chat so people can figure out who I am and what I've been doing and why I'm interested in time and causality. It's a very complex and difficult problem. So good. Thank you, everyone. I think 2 more weeks from now, there's another presentation. Is that correct, Ahmed?
Yes, there will be a presentation about optical networks.
Good. Excellent. Thank you very much, everyone. Nice to see you here. I was taught by my CEO at Sun Microsystems to always close meetings down on time. and so I'm happy to be able to do that 2 minutes before the top of the hour. Thank you, everyone. Take care.
Thank you. Thanks.
Bye.
Thank you.